Hello, welcome back. So now in this part, we will solve an example. So this is the problem that we have to solve. In this, it is saying determine the reinforcement required of a ring beam of width B as 400 mm, effective depth of beam is 650 mm, overall depth of beam is 700 mm, and it is subjected to a factored bending moment as 200 kilonewton meter and a factored torsional moment is 50 kilonewton meter and factored shear force as 100 kilonewton meter, and we have to use M20 grade of concrete and Fe415 for the design. Now if we draw the sketch for this, it will something look like this. So for the reference purpose, I am just showing you the reinforcement here because effective depth is measured from the center of the bar to the topmost fiber. So this is 650. Overall depth of the beam is 700 mm and the width of beam is 400 mm. Now this is actually a ring beam. So this ring beam can be of any overhead tank. So as I explained earlier also, ring beams are generally subjected to torsional moment, and therefore we now need to find out the reinforcement for this beam. But before we start our solution, first of all we will see how many steps are there. So basically there will be 7 steps for this problem. So in the first step, first of all we have to check whether the cross-sectional dimension, specifically the depth of beam, whether it is sufficient or not. Well, we can check the depth of beam by comparing the value of tau VE and tau C max. So as I explained earlier also that if the value of tau VE is less than tau C max, then we say that the depth of beam is fine. If it is more than that, then we have to increase the cross-sectional area or increase the grade. So as I explained here, in the first step, we will first check the sufficiency of the depth of beam by comparing tau VE and tau C max. Now, we can calculate tau VE only when we are able to find out the value of VE, which is the equivalent shear force. So equivalent shear force can be calculated by this formula, as I explained earlier also. And in this, we have value VU, TU. So VU and TU both are given in our problem. B is the breadth of beam. So putting all the value. So here you can see VU is given in kilonewton, TU is given in kilonewton meter, and that is why I have taken the value of B as in meter. It is given as 400 mm, but I have taken this as 0.4 meter because I am required to find out VE in terms of kilonewton. So therefore I am using the same unit for that. So TU is having unit kilonewton meter. So that is why I have taken the value of B as in meter. So solving this, we get the equivalent shear force as 300 kilonewton. Now we have got the value of VE. Now we can calculate the value of tau VE. So tau VE is VE upon B into D. B is 400, D is 650, which is already given in the question. So putting all, now here we have to take care of the units as we are supposed to find out tau VE. Now what is tau VE? Tau VE is equivalent shear stress. So whenever we are required to find out stresses, we will have our values in Newton and mm. So VE is the shear force. So the unit of shear force is in kilonewton. So we have to convert this into Newton. Similarly, B and D will be putting in terms of mm. So putting all the values here, we calculate the tau VE as 1.154 Newton per mm square. So now we have found the action of load as a stress. Now we will compare this tau VE value with the tau C max. Now the value of tau C max can be found from the table 20. So I will show you the table 20 there. So in the IS code, so this is table 20, which is on page number 73. So there you can see value of maximum shear stress, which is tau c max. It is dependent on the grade of concrete. So we are using grade of concrete as M20. So for M20 grade of concrete, the value of tau c max is 2.8. So now if we go to the slide, so there you can see the value of tau VE is 1.154 and it is less than the value of tau C max. So therefore we can say that the section does not need any revision and therefore the depth of beam is okay. So as the value is less than this, depth of the beam is okay. So that completes our step 1. Now we will go to the next step. We have to now check whether the torsional reinforcement in the beam is required or not. Now torsional reinforcement in the beam can be checked by comparing the value of tau VE with tau C. So as I have written here, to check the torsional reinforcement requirement, we will now be comparing to tau VE, tau C and tau C max. Now we have already calculated tau C max. We have already find out tau VE. Now we will be finding the value of tau C. Now tau C is called permissible shear strength of the concrete. And this permissible shear strength of concrete, it actually depends on the percentage of tension reinforcement. Now, for the time being, we don't know what percentage of tension reinforcement there be in the beam because we are required to find out that. So therefore, now we have to assume the percentage of tension reinforcement. Generally, we assume 0.5% of the tension reinforcement. Generally, in our problem, we generally assume that 0.5% of the tension reinforcement. And now based on this value, now we will find out the value of tau C from table 19. Now again, I will show you this table 19 in the IS code. So here you can see above table 20, there is table 19, which is for tau C. As you can see here, tau C is dependent on the percentage of steel, which is 100 into AS by BD. AS is the percentage of tension steel. B and D is the width and the effective depth of the cross sectional. So here we have assumed that percentage of tension reinforcement as 0.50 and we are using grade M20. So corresponding to this, we have value of tau C as 0.48 for this. So therefore, now we will see that on our slide. So here the value of tau C is 0.48 and we can say that this value is less than the value of tau VE because tau VE is 1.154 and tau C max is 2.8. So tau C is less than tau VE. So this is the condition 4, which I have discussed in the IS code provision. So in the case 4, we are now required to find out longitudinal and transverse reinforcement for the beam. So now we will calculate longitudinal and transverse reinforcement because of this condition, because tau C is less than tau V is less than tau C max. Now in the step 3, now we will calculate the longitudinal tension reinforcement. So longitudinal tension reinforcement will be calculated for the equivalent bending moment, that is ME1, and the formula for ME1 is MU plus MT, MU plus MT. So MU value is already given in the question. We are required to find out MT. So ME1 is MU plus TU bracket में 1 plus D by B upon 1.7. So MU, as I said, it is already given in the question. So we will directly put the value, but we will calculate the value of MT, which is already given in the IS code I have mentioned earlier. So putting all the values here, so 200, it is already given there, and D by B, Either we put that in mm or in meter. We simply need to find out the ratio of that, and then we will be able to calculate the value of me1, which is 280.88 kilonewton meter. So we have to design reinforcement for this moment. But before designing the reinforcement, first of all, we have to find out whether our this beam section is under reinforced section or over reinforced section or the balanced section. So that is what I have written here. Before we calculate longitudinal tension reinforcement for this moment, we need to determine whether our beam is under reinforced, balanced or over reinforced section. Now, how do we compare? How do we find out whether our section is under reinforced, balanced or over reinforced? Basically, generally by comparing the depth of neutral axis. So there is basically two depth. One is the actual depth, which we represent as xu, and the other one is maximum depth of neutral axis. So maximum permissible depth of neutral axis, we represent that as xu max. So this is the maximum limit of depth of neutral axis, and xu is the actual depth of neutral axis. So by comparing this, we determine whether our section is under, over or balanced. So when the actual depth of neutral axis is less than xu max, then we say that our beam is under reinforced. Similarly, if the value of xu is more than xu max, then we say that the section is over reinforced. And when the value of xu is equals to xu max, then the section is balanced. So now, first of all, we need to find out the value of xu and xu max. Now, the value of xu max can be determined using the IS code, and that I will show you in the IS code also. So here in the IS code, if we go to page number 70, basically the value of xu max is dependent on the grade of steel. As we are using Fe415, the ratio of xu max by d is 0.48. So we can say that for Fe415, the xu max by d is equals to 0.48, or xu max is 0.48 times of d. Now d is already given in the question. Now multiplying this with 0.48, we can find out the maximum depth of neutral axis. So that we will see on our slide. So the maximum depth of neutral axis is 0.48 times of d, which we have found from the IS code, and putting the value, we get maximum depth of neutral axis as 312. Now we have found the value of xu max. Now we have to find out xu. Now basically in the IS code, there are two formula given for the bending moment strength or moment of resistance of under reinforced and over reinforced and balanced section. So basically actual depth of neutral axis can be calculated using the relation. So the formula is also given in the IS code. So now I will show you the formula for actual neutral axis, depth of actual neutral axis. So here in the IS code, if you go to page number 96 on this annexure G, then there you can see if we refer to this clause, which is G1. So in this case, to determine the depth of neutral axis from the following equation. So we can determine the value of xu from this equation. So which says xu by d is equals to 0.87 Fy into AST upon 0.36 FCK into B into D. So if we cancel t by this, we actually get formula to calculate the value of xu. But there is a problem in this formula, and that the problem is that the formula is having a variable ast. Now ast is the area of steel. So to calculate the value of xu, we need to find out ast first, then only we will be able to find out the value of xu. Now the value of ast can be calculated, but before that we have to assume uh, whether our section is under or over, because if we scroll down, then you see this formula. Mu is the moment of resistance of under reinforced section, and moment of resistance of under reinforced section can be calculated with this formula, which is 0.87 into Fy into Ast into D, and in the bracket it is 1 minus Ast into Fy by Bd into Fck. So using this relation, we can find out AST, but this relation is for the under reinforced section. Similarly, if we consider that our section as over reinforced section, so for that, moment of resistance formula is provided in the C part, which is mu limiting. So maximum moment of resistance is represented as mu limiting is equals to 0.36 times of xu max by d. In the bracket it is 1 minus 0.42 xu max by d. Outside bracket it is bd square by bd square into fck. So now we have option, either we use B formula or the C formula. Generally, as we always want our section to be under reinforced section, so therefore we will take this relation, and with this relation we will first find out the value of AST, and then once we find out the value of AST, then we put the value in this equation. Sorry Yes. So then we will put the value here in this equation, and then we find out the value of xu, and then we will compare with xu max. So that is the process that we are going to follow on our slide. So here actual depth of neutral axis can be calculated by this formula, and in this AST is not known. So for that AST, we will assume that the section is under reinforced, and we will now use the relation to calculate the value of AST. Now, as you can see, this mu is actually the bending strength or moment of resistance of the beam, which is generally subjected to bending and shear force only. But as we are designing a beam which is subjected to torsion along with bending moment and shear force, so the moment of resistance, we are representing that as me1, or the moment we are representing as me1. So here in this formula, we will replace mu with me1, and the right hand side will be as it is. So replacing mu as me1, then we have this. So putting all the values, 280 into 280.88 into 10 to the power 6. So we will, as AST will be required in mm square. So therefore we have to put all the values in Newton and mm. So putting all the value, solving the equation, this equation will be as a quadratic equation. So when we solve this, we will have a quadratic equation, and solving the quadratic equation, we can find out the value of AST as 1340.56 mm square. Basically, there will be two values of AST. One will be very higher one, and the second one will be the lower one. So this one is the lower one value. So we will, or there may be chances that you may get negative value. So negative value has no significance. So therefore, we will adopt a positive value. So the AST is 1340.6.56. So now we will put this value in the equation of xu, and then we will now find out the value of xu as, now in this formula we will put all the values. So you can see the value of XU is 168.05, which is less than 312 mm. Now you can see our aim was to find out longitudinal tension reinforcement, and as we have assumed our section is under reinforced section, and it is actually under reinforced section, which proves this, that XU is less than XU max, which means the AST that we have calculated earlier, it will be our area of reinforcement for the tension side. So hence the section is under reinforced, and therefore the value of AST is valid. Why? Because the section is under reinforced. It is now confirmed here. Now, as the AST value is calculated, we have to distribute this area into the number of bars. So how many number of bars will be there? That is being calculated by using this formula. Total area of steel divided by area of cross section of one bar. So AST is the total area, A phi is the area of cross section of one bar. Now, for calculating the area of cross section, we need to assume the dia of bar. So now say assuming the dia of bar as 20 mm. Say we are assuming 20 mm dia bar. So putting the value here, this is the AST and this is the area of cross section of one bar. We get the number of bar as 4.23. So generally we don't provide bars like this. We can't provide 4.23 bars. So basically we will say that we are providing roughly 5 bars for that. So as you can see that this is the required number, but we are providing more than required, which means the area of steel provided will be more than this area. The area of steel that we will be providing will be more than this area. So that we will see what will be the area of steel. So area of tension reinforcement provided, how much? Number of bars multiplied by area of cross section of one bar. So basically we have provided 5 bar. So 5 bar multiplied by area of cross section of one bar. So the total area of steel that we have provided is 1570 mm square. So total area of bar is this one. So that is the tension reinforcement that we have provided in the steel. Now we have to check whether this area is less than or more than the limit that is being recommended by the IS code, and also we will see what is the percentage of this reinforcement. So because in the second step we have assumed percentage of steel as 0.5% to calculate the value of tau c. So here we need to check whether the assumed value is near to the actual value or not. So for that we are now calculating the percentage of steel. So percentage of steel can be calculated by this relation: total area of steel provided divided by the effective cross sectional area whole multiplied by the 100. So with this we can find out the percentage of steel as 0.6%. So you can see we have assumed percentage of steel as 0.5%, but here the actual area of steel is 0.6%, which means for 0.6% the value of tau c will also be different. Now value of tau c from the table 19, if we again refer to the table 19, then the value of tau c will be different. It is slightly more than the value that we have taken, because for 0.5% tau c was 0.48 Newton per mm square, and for 0.6% the value of tau c is 0.51 Newton per mm square. But you can see this value is still less than, it is still less than tau VE. So therefore we still be required to provide torsional reinforcement, which means adoption of 0.5 is more or less fine. Okay, because we have assumed just to check whether we are required to provide torsional reinforcement or not. So this also confirms that we will be required to provide torsional reinforcement, and that is what we are now providing. Okay, so this is what we are required to check. Now we will check the minimum area of tension reinforcement as recommended by the IS code. So as per clause 26.5, the minimum tension area can be calculated by this relation which is given in this clause. So putting all the values, we get the minimum area of steel as 532.53 mm square. While we have provided this area and minimum area to be provided is 532, which means this is more than the minimum area required. So which means our reinforcement area is okay. So as you can see, it is less than AST provided. So therefore we can say that it is more than the minimum requirement. Similarly, if we check the maximum tension reinforcement, we can calculate this with this relation, which is 0.04 times of B into D. So putting all the value here, we get maximum tension reinforcement as 11,200. So you can see our AST provided is less than this value, which means our AST provided is more than minimum and less than maximum limit as recommended by the IS code, which is safe and which is okay. So we will continue this solution in the next part. Thank you.